In the summer of 1995, in the city of Hyderabad, India, a group of engineers walked into a building that had no air conditioning, no fans, and no mechanical cooling of any kind. Outside, the temperature was pushing 108 degrees Fahrenheit. Inside, it was 72. They checked their instruments twice, because the readings didn't make sense. The walls were made of fired clay. The roof was embedded with clay pots. And the whole thing had been built for less than a third of the cost of a comparable concrete structure. That 36-degree difference wasn't a fluke. It was physics, ancient physics, working exactly as designed. What those engineers found in 1995 wasn't new. The technique of embedding clay pots into roofs and walls to passively cool buildings had been practiced across South Asia, the Middle East, and North Africa for more than 2,000 years. But somewhere in the 20th century, as concrete and steel became the default language of construction, this knowledge got quietly buried. Today, roughly 87% of new residential buildings in hot-climate urban centers are built with solid concrete roofs, the single worst thermal choice you can make in a hot, dry environment. And utility companies couldn't be happier about that. So the question this video is going to answer is this: how does embedding clay pots into a roof actually drop interior temperatures by up to 50% without a single watt of electricity? And if this technique is that effective, that cheap, and that well documented, why are you not seeing it in new construction across Arizona, Texas, Spain, or Morocco? Those aren't rhetorical questions. We're going to answer both of them precisely, with real numbers and real failure modes. Because the honest answer is more interesting and more useful than the simple one. Let's start with the problem you already know, because you've felt it. You walk into your home at 6 in the evening, after the sun has been beating on your roof all day, and it's actually hotter inside than it was at noon. You crank the air conditioning, and it runs for 3 hours before the space finally feels livable. That isn't your system failing. That's your roof, doing exactly what a solid concrete slab does best. It absorbs heat all day, like a thermal battery, and then it slowly releases that stored energy downward, directly into your living space, for hours after sunset. A standard 4-inch concrete slab roof can store enough thermal energy by mid-afternoon to keep radiating heat into a home until well past midnight. Studies from the Indian Institute of Technology have measured interior surface temperatures on the underside of unshaded concrete roofs reaching 104 degrees Fahrenheit in peak summer, at 7 in the evening, 2 hours after the sun has already started to drop. That's the roof acting like the inside of a slow cooker. Your air conditioner isn't fighting the outside air anymore. It's fighting your own building materials. In hot climates, roofs account for up to 70% of total heat gain in a single-story building. Not walls, not windows, the roof. Because it sits horizontal, under the most direct angle of solar radiation for the longest part of the day. A south-facing wall gets oblique sun. A flat roof gets perpendicular sun from 10 a.m. to 3 p.m., absorbing at maximum efficiency. The material you choose for that roof isn't a cosmetic decision. It's the single biggest thermal decision in the entire building. And for most of the 20th century, we almost universally made the worst possible choice. Now here's where the history starts. In the early 1980s, an architect named Satprem Maini was working in Auroville, the experimental township in Tamil Nadu, southern India. Auroville was founded on a philosophy of sustainability and self-sufficiency, which in practical terms meant building without imported materials and without energy-intensive systems. Maini wasn't trying to revive ancient technology for romantic reasons. He was working with a construction budget that made air conditioning economically impossible, and he needed to keep buildings cool in a climate where summer temperatures regularly exceed 100 degrees Fahrenheit. The constraint was financial, not philosophical. Maini's team began studying traditional vernacular building techniques from across the region, the kind of knowledge that still lived in the hands of older craftsmen but had been systematically displaced by the post-independence push toward modernist concrete construction. What they found, documented in villages and older urban neighborhoods across Tamil Nadu and Andhra Pradesh, was a practice of filling the dead space in roof structures with inverted clay pots, locally made, inexpensive, and fired at low temperature. The pots weren't structural. They weren't decorative. They were doing something far more sophisticated. They were making the roof thermally invisible. This wasn't Maini's invention. He was the person who documented it rigorously, tested it against modern controls, and brought it into the vocabulary of contemporary architecture. But the technique itself is ancient. Archaeologists have found evidence of clay pot void forming in Roman construction. The Romans used amphorae embedded in concrete vaults to reduce weight and improve thermal performance. Most famously, in the Dome of the Pantheon in Rome, built around 125 AD. The same principle appears in Islamic architecture across North Africa, in Persian wind towers, and in the traditional courtyard homes of Rajasthan. This idea has been independently rediscovered on at least 4 continents. So what is actually happening, physically, when you embed a clay pot in a roof slab? Let's walk through the mechanism one step at a time, because it's elegant and it's not obvious. A standard concrete roof is a solid, homogeneous mass. Heat enters at the top surface, conducts through the material, and emerges at the bottom surface. The rate at which it does this is determined by 2 properties of concrete: thermal conductivity, which is how fast heat moves through it, and thermal mass, which is how much heat it can store before it starts transmitting. Concrete scores high on both, which is exactly the problem. When you embed clay pots, inverted, mouth down, into that concrete slab before it cures, you replace a portion of the solid concrete volume with sealed air pockets. Air is one of the best natural insulators that exists. Its thermal conductivity is roughly 40 times lower than concrete's. So each pot-shaped void becomes a thermal break, a barrier that heat has to go around, not through. The roof is no longer a solid conductor. It becomes a porous, interrupted matrix where heat pathways are fragmented and slowed dramatically. Think of it like replacing a solid metal pan with one that's full of air bubbles. Same size, fraction of the heat transfer. The clay itself also contributes. Fired terracotta has a thermal conductivity of roughly 0.8 watts per meter Kelvin, compared to concrete's 1.6 to 2.0. So even the pot walls are conducting heat at half the rate of the surrounding concrete. And because the pots are hollow, the effective thermal mass of the roof is dramatically reduced. You've replaced dense, heat-storing concrete with air and low-density clay. The roof now has less capacity to absorb and hold heat. It charges slower in the morning, it discharges less in the evening, and the peak load that reaches your ceiling at 7 p.m. is a fraction of what a solid slab would deliver. There's a secondary mechanism that most summaries miss, and it's important. Clay is a porous material. Even fired clay retains a degree of microporosity. In conditions of moderate humidity, the outer surface of an embedded clay pot can undergo slow evaporative cooling. Moisture migrates through the pore structure and evaporates at the surface, absorbing latent heat in the process. This is the same physics that makes a terracotta water pot cooler than ambient air on a dry day. In a roof context, this effect is modest. We're talking about a 2 to 4 degree Fahrenheit contribution, but it adds to the insulative effect and it costs nothing. Now let's look at the data, because that's what makes this real. In 2003, the Building Materials and Technology Promotion Council of India, working with the Central Building Research Institute, conducted a controlled comparison between 2 otherwise identical single-room structures in Roorkee, one with a conventional concrete slab roof, one with a filler slab using clay pots. Same floor area, same wall construction, same orientation, same local climate. They monitored both structures over a full summer cycle and measured temperatures at multiple points: outer surface, inner surface, and ambient interior air. The results were consistent across the monitoring period. The inner ceiling surface of the clay pot filler slab ran 13 to 18 degrees Fahrenheit cooler than the equivalent surface in the conventional concrete structure. The interior air temperature difference was 8 to 12 degrees Fahrenheit at peak, which occurred between 6 and 8 p.m., the hottest interior hour in both structures. But here's the more important detail. In the conventional structure, the interior peak temperature arrived at 7:30 p.m. on average. In the filler slab structure, the attenuated peak arrived at 9:15 p.m., nearly 2 hours later, and significantly lower. By then, ambient outdoor temperatures had already dropped, and natural ventilation could handle the remaining load. That time shift is actually the most valuable part of the performance, more than the raw temperature reduction. An air conditioning system, sized for a 95-degree interior load, is a very different machine from one sized for an 83-degree load that arrives 2 hours after sunset. The first one runs continuously through the hottest hours. The second barely needs to switch on. In a 1,500 square foot single-story home in a hot, dry climate, that thermal delay alone translates to a reduction in cooling energy demand of 30 to 45% over a full summer season. At current U.S. electricity rates, that's $400 to $700 per year off a typical summer utility bill. Every year, for the life of the building. The material savings are equally striking. A filler slab roof using clay pots replaces 20 to 35% of the concrete volume in the slab. Concrete is the most energy-intensive and expensive component of a conventional roof. Removing 30% of it doesn't just reduce material cost, it reduces the weight of the roof structure, which reduces the load on beams, columns, and foundations. A 2002 study from Anna University in Chennai calculated that a clay pot filler slab roof for a 1,000 square foot home saved approximately 1,800 kilograms of concrete, reduced structural steel requirements by 15%, and cut construction cost by 23% compared to a solid slab of equivalent span. The embodied carbon story is compelling too. Portland cement, the binding agent in concrete, is responsible for approximately 8% of global CO2 emissions. Every ton of cement clinker produced releases roughly 0.9 tons of CO2. A clay pot filler slab, by reducing concrete volume by 25 to 30% per structure, directly cuts the embodied carbon of the roof by a proportional amount. In a mass housing project of 500 units, the scale at which this technique typically gets deployed in India, that's a reduction of approximately 900 metric tons of CO2 equivalent per project. That's the annual carbon footprint of about 100 native American households, eliminated at zero operational cost. Real-world deployment data backs up the lab results. The city of Puducherry, in southern India, formerly Puducherry, has had a municipal building policy encouraging filler slab construction in public housing since the mid-1990s. A monitoring study conducted there in 2008 across 47 monitored residential units found that occupants in filler slab homes ran mechanical cooling systems for an average of 2.3 fewer hours per day compared to neighbors in conventional concrete homes, a reduction of 38% in daily cooling hours. Occupant-reported thermal comfort scores were also higher in the filler slab buildings, even on days when both groups used no mechanical cooling at all. So here's the pivot point in this video. We've just established that clay pot filler slab construction is cheaper to build, significantly cooler to live in, measurably lower in embodied carbon, and documented across centuries and continents. It's been proven in controlled studies and monitored across real housing at city scale. And it's available using materials that, in most of South Asia and the Middle East, cost less than 5 cents per unit. Given all of that, why is this technique not showing up in new construction in Phoenix, in Seville, in Riyadh, in any of the high-heat urban zones that need it most? The answer is 4 problems, and they compound. The first barrier is labor economics, and it's the most immediate. Clay pot filler slab construction is hand-intensive. The pots must be placed individually, by hand, into a steel reinforcement cage, at correct spacing and orientation, before the concrete pour. A typical 1,000 square foot roof requires approximately 350 to 500 pots. Placing them correctly, inverted, evenly spaced, tied to prevent floating during the pour, takes a trained crew roughly 4 to 6 hours. In India, where this labor costs $5 to $8 per worker per day, that's a manageable addition to the project budget. In the United States, where skilled concrete labor runs $55 to $80 per hour, that same 4-hour placement task adds $1,200 to $2,000 to the cost of a single roof. That labor premium doesn't eliminate the lifetime savings. Remember, we calculated $400 to $700 per year in cooling cost reduction. At that rate, even a $2,000 labor premium pays back in 3 to 5 years. But construction economics don't work on lifetime payback for the builder. The person building the house often isn't the person paying the utility bills. A developer building spec homes has no financial incentive to spend $2,000 extra upfront for a benefit that accrues to the buyer over a decade. This misalignment between who pays the upfront cost and who captures the long-term savings is the single most common reason passive building techniques fail in the market, regardless of how effective they are. The second barrier is supply chain. Clay pots for filler slabs are not standard terracotta flower pots. They have specific requirements: a consistent internal volume of roughly 3 to 5 liters, a firing temperature that achieves adequate strength without overfiring to the point of reduced porosity, a wall thickness of 8 to 12 millimeters for structural compatibility, and a rim geometry that allows correct inversion and seating in the reinforcement grid. In Tamil Nadu, these pots are produced by a network of traditional potters who have adapted their output to these specifications over decades. In the American Southwest or Southern Europe, that supply chain simply does not exist. Could you import them? In theory. Unglazed terracotta is a low-value commodity. The pots themselves cost pennies to produce. But shipping cost and import logistics raise the delivered price dramatically. A pot that costs 4 cents in Tamil Nadu arrives in Phoenix at roughly $1.80 to $2.40, before contractor markup. At 400 pots per roof, you're at $720 to $960 in materials before you've touched labor. That's not prohibitive, but it converts a locally resourced, cheap technology into an imported specialty product, which changes its economic identity entirely. And specialty products require specialty supply chains, which require volume, which requires adoption, which doesn't exist yet. It's a classic chicken and egg problem. The third barrier is building codes, and this one is genuinely frustrating. In the United States, building codes are based on prescriptive standards, specific, approved methods and materials. Filler slab construction is not listed in any current version of the International Building Code or the International Residential Code. To build one legally, you need to go through an alternative materials and methods review, which typically requires engineered drawings stamped by a licensed structural engineer, a materials testing report, and approval from the local authority having jurisdiction. In practice, that process costs between $8,000 and $25,000 in engineering and filing fees alone, before you've poured a single cubic yard of concrete. In Europe, the situation is slightly better. Several countries, Spain, Portugal, and Italy in particular, have historical precedent for clay pot concrete roof construction under local building traditions, and some regional codes accommodate it. But accommodate is not the same as endorse, and most contractors won't take on an unfamiliar method that adds liability exposure when a conventional solution exists. The regulatory and liability environment essentially creates a financial penalty for innovation, even when the innovation is 2,000 years old. That's a systemic problem that no amount of performance data fixes quickly. The fourth barrier is the hardest one, because it's physics, and you can't negotiate with physics. Clay pot filler slabs are vulnerable to freeze-thaw cycling. Any porous material, and the clay pots in a filler slab are, by design, slightly porous, will absorb trace moisture over time. In climates where temperatures cycle repeatedly below 32 degrees Fahrenheit, that moisture expands as it freezes, generating internal pressure that eventually fractures the clay. A single winter in Chicago or Denver will begin degrading unprotected clay pot voids within the roof slab. After 5 to 10 freeze-thaw cycles, the structural integrity of those voids is compromised, and the roof has to be evaluated. This is the non-negotiable dealbreaker. Filler slab construction with clay pot voids is a warm climate-only technology. It works reliably in USDA hardiness zones 9 through 13. Roughly, the southern band of the United States from Central California to Florida, the entire Gulf Coast, Hawaii, and Puerto Rico. It works brilliantly across South and Southeast Asia, the Middle East, North Africa, and Southern Europe. The moment you take it north of the frost line and expose it to real winter cycling without an exceptional waterproofing system, you are accepting accelerated deterioration. Be honest about that. This is a hot climate-only, new construction-only tool. In those zones, it's exceptional. Outside them, it isn't appropriate. So now let's talk about how you actually do this correctly, because knowing the physics isn't enough. There are specific failure modes that show up even in favorable climates, and most of them are avoidable with simple procedural discipline. The first critical error is using dry, unsoaked pots. When you place a dry clay pot into a fresh concrete pour, the porous clay immediately begins wicking water from the cement slurry. This localized dehydration weakens the cement matrix immediately surrounding each pot. The bond between pot and concrete is compromised, and the structural assumptions of the slab are no longer valid. Every clay pot must be soaked in water for a minimum of 2 hours before placement, not dampened, soaked, until the absorption rate visibly slows. The second common failure is incorrect concrete vibration during the pour. A filler slab requires a concrete vibrator to consolidate the mix around and between the pots. You need to eliminate air pockets in the structural concrete, not in the pots. The vibrator must never contact a clay pot directly. Direct contact transmits enough energy to crack or shatter the pot. You'll hear a dull pop, and you've just collapsed a void that was supposed to be there. The vibrator should be inserted between rows of pots, never over them. This requires a slightly modified vibration pattern that takes an experienced operator about 2 hours to learn. It's not complex, but it must be taught, not assumed. The third error, and the one that quietly destroys long-term performance, is failing to seal the underside of the finished slab. A filler slab roof that is left with an exposed concrete soffit will eventually allow atmospheric moisture to enter the microcracks that develop in any concrete over time. Once moisture finds a path to the clay pot voids, you're looking at a slow evaporative cycle that, in humid climates, can lead to mold within the void spaces, and in cold climates, the freeze-thaw damage we already discussed. The correct specification is a minimum 12 to 15 mm application of hydraulic cement plaster on the underside of the slab, applied within 48 hours of curing, before any moisture infiltration pathway can develop. There's a fourth detail that rarely appears in documentation but comes up consistently in field reports from projects in Oroville and across Tamil Nadu. The top surface of the filler slab, the exposed roof deck, must be finished with a high albedo reflective coating. Without it, you've improved the thermal resistance of the roof dramatically, but you've done nothing about solar absorptance at the surface. A dark or uncoated concrete deck in full sun can reach 160 to 180 degrees Fahrenheit in peak summer, a temperature differential so extreme that even the insulation of the clay pot voids is partially overwhelmed. A white lime wash or reflective roof coating costs less than 50 cents per square foot and drops surface temperature by 40 to 60 degrees. It's the cheapest amplifier of an already effective system. Let's put the complete picture together, because the system effects compound in a way that isn't obvious until you trace them through. A correctly built clay pot filler slab roof with pre-soaked pots, correct vibration technique, sealed soffit, and reflective top surface delivers the following: a peak interior ceiling surface, temperature 15 to 20 degrees Fahrenheit, lower than a conventional slab. A thermal peak delay of 1.5 to 2.5 hours, shifting the maximum interior heat load from mid-evening to late night. A construction cost reduction of 18 to 25% versus a comparable solid slab, and a 30 to 45% reduction in mechanical cooling energy over a full summer season. These aren't independent benefits. They stack. The stacking effect is worth dwelling on, because it illustrates why this technique is more powerful than it looks on paper. The reduced peak temperature means your air conditioning compressor starts from a lower baseline. The time delay means it starts running when ambient outdoor temperatures are already falling, so it's fighting a diminishing load rather than a growing one. The lower indoor surface temperature reduces radiant heat transfer to occupants. The heat your body feels from a hot ceiling isn't just air temperature, it's infrared radiation from that surface. A ceiling running 18 degrees cooler feels dramatically more comfortable at the same air temperature, which means you set the thermostat higher and save additional energy. The effect is multiplicative, not additive. This multiplicative performance is what caught the attention of the National Institute of Urban Affairs in India in the early 2000s. The NIUA began a systematic effort to document and standardize filler slab technology for inclusion in Indian National Building Guidelines, a process that eventually resulted in the technique being referenced in the Energy Conservation Building Code issued by the Bureau of Energy Efficiency in 2007. That code reference was the inflection point. It gave architects and engineers a regulatory basis to specify filler slabs without requiring a one-off alternative materials review for every project. By 2015, an estimated 40,000 to 60,000 homes in India had been built using some variant of the filler slab technique. But India isn't the only place where this is gaining traction. In the early 2010s, a team from the Hassan Fathi Foundation, honoring the Egyptian architect who spent his career reviving vernacular passive cooling techniques for the rural poor, began testing clay pot roof inserts in new construction across Upper Egypt. The climate there is extreme. Summer temperatures regularly exceed 110 degrees Fahrenheit. Humidity is low, and mechanical cooling is either unaffordable or impossible for the majority of the population. The results from monitored units in Luxor Governorate showed interior temperature reductions of 19 to 22 degrees Fahrenheit, compared to standard brick and concrete construction. That's not a comfort improvement. That's a survival improvement. Hassan Fathi himself deserves more than a passing mention here, because his career embodies the intellectual lineage this technique sits within. Fathi was an Egyptian architect who graduated from Cairo University in 1926 and spent the following 5 decades arguing, against enormous professional resistance, that the passive cooling techniques embedded in traditional Islamic and Nubian architecture were not relics of poverty, but sophisticated engineering solutions that modern construction was abandoning at enormous cost. His 1969 book, Architecture for the Poor, documented dozens of specific techniques: wind catchers, courtyard geometry, thick mud brick walls, roof shading, that collectively kept buildings 20 to 30 degrees cooler than ambient in the Nile Valley's brutal summer. Fathi's work was dismissed by much of the mainstream architectural establishment during his lifetime as nostalgic primitivism. But the climate crisis and the energy crisis have a way of rehabilitating inconvenient ideas. The passive cooling techniques he documented are now being actively studied by climate adaptation researchers at institutions including MIT, ETH Zurich, and the Indian Institute of Technology. The phrase vernacular wisdom has become respectable in engineering circles in a way that would have seemed remarkable in 1975. And the filler slab is a perfect example of that category, a technique that was never lost, just ignored, while the world built thermal disasters out of reinforced concrete. Let's zoom out and look at where this fits in the broader landscape of passive cooling strategies. Because filler slab doesn't exist in isolation. It's one technique in a toolkit that includes roof gardens, cool roof coatings, radiant barriers, thermal mass with night purging, cross-ventilation design, and evaporative cooling systems. Each technique has a climate niche. Filler slabs are specifically optimized for hot, dry to semi-arid climates, with high solar radiation, low humidity, and large diurnal temperature swings. The conditions where the thermal time shift benefit is most valuable, because cool nights exist to exploit it. In hot, humid climates with small day-night temperature differences, the time shift is less useful, and other strategies take priority. The combination that performs best in field studies is a filler slab roof plus a roof garden plus a reflective top coating. The roof garden adds an evaporative cooling layer at the top surface, dropping the concrete deck temperature before heat even enters the slab. The filler slab slows and attenuates the heat that gets through. The reflective coating reflects a large fraction of solar radiation before absorption begins. Monitored buildings in Bangalore using this combination have recorded interior temperatures 24 to 27 degrees Fahrenheit below ambient on peak summer days, without a single watt of mechanical cooling. At those performance levels, in most of the inhabited regions of the tropics and subtropics, you have effectively eliminated the need for air conditioning for the majority of the year. That last point is worth sitting with for a moment. Eliminating the need for air conditioning for the majority of the year is not a technical claim most engineers make casually. We don't make it casually either. In a climate like Bangalore's, where temperatures exceed the comfort threshold for roughly 90 days per year, a building that stays within the comfort range through passive means alone for 75 of those days has reduced its mechanical cooling requirement by 83%. Not improved it, not optimized it, reduced it by 83%. That changes the scale of the system you need to buy, the electricity contract you need to sign, and the carbon you're responsible for over the life of the building. Now let's talk about what this looks like in practice for someone who wants to actually use this technique, not hypothetically, not in a research paper, but in a real building project. The first thing to understand is that filler slab construction works within the standard reinforced concrete structural framework that most builders in warm climates already use. You're not replacing your structural system. You're modifying your roof slab within the same formwork, the same reinforcement schedule, and the same pour sequence. The only additions are the pots themselves and the modified vibration procedure. This is important because it means the technique can be adopted incrementally, one contractor, one project, one building at a time. The structural design of a filler slab requires attention to a few critical parameters. The concrete between pot rows must maintain a minimum thickness. The ribs and the top and bottom cover layers together must satisfy standard structural requirements for moment and shear. As a rule of thumb used in Indian practice, the pot diameter is typically 65 to 70% of the slab depth. The rib width between pot rows is minimum 100 millimeters, and the structural concrete cover at the bottom is minimum 20 millimeters. These numbers ensure that the load-bearing performance of the slab is maintained despite the reduction in concrete volume. Deviating from these proportions is how you get a roof that cools but doesn't carry load. The choice of pot geometry matters more than most guides acknowledge. Spherical or hemispherical pots are the traditional form, but elongated or cylindrical forms, sometimes called pot tiles, have been used in East African and some Middle Eastern applications. The cylindrical forms pack more efficiently, reducing the concrete volume fraction further, but they create unidirectional ribs rather than a bidirectional rib grid. A bidirectional rib grid is structurally superior because it distributes loads in two planes simultaneously. Hemispherical pots naturally produce a quasi-bidirectional rib pattern. If your local supply offers only cylindrical forms, a structural engineer familiar with one-way joist slabs needs to be involved in the design. The concrete mix design for a filler slab is also slightly different from a standard roof pour. Because the vibrator can only access the spaces between pot rows, the mix needs higher workability, typically a slump of 100 to 125 millimeters rather than the 75 to 100 millimeters standard for a conventional flat slab. This is achieved by adjusting the water-cement ratio carefully upward, but not past 0.50 without adding a plasticizer, because excessive water weakens the hardened concrete. Many practitioners in India use a simple rule. If the concrete flows easily to fill around the pot sides without direct vibrator pressure, the workability is correct. If it needs to be pushed around the pots, add a small dose of superplasticizer before increasing water. Let's talk about sourcing and substitution, because this comes up in every serious conversation about adopting this technique outside South Asia. If locally produced, specification-appropriate clay pots are not available, what are the alternatives? The most commonly discussed substitution is expanded polystyrene, EPS, void formers, which are manufactured to precise specifications and are already used in some commercial waffle slab systems. EPS has very low thermal conductivity, around 0.04 watts per meter Kelvin, compared to clay's 0.8, so it performs better as a pure insulator. But it eliminates the evaporative cooling contribution of clay, and its embodied carbon is significantly higher. It also floats aggressively during a concrete pour, requiring mechanical restraint that clay pots don't need. A more promising local substitution, and this is where the research frontier is right now, is low-fire terracotta tile pieces, broken ceramics, or purpose-fired local pottery adapted to the specification. A 2018 research paper from the University of Nairobi tested standard small terracotta flower pots, the type available in any garden supply store across East Africa, as filler slab inserts, with the pots cut to uniform depth with a masonry saw. The performance results were comparable to standard filler slab construction, within 5% of the temperature reduction values, and the pots were sourced entirely locally at a cost of 8 cents each. This substitution approach, adapt a locally abundant ceramic product to the specification, is the pathway that makes this technology globally transferable. The research from Nairobi is significant beyond its technical results, because it demonstrates a principle that applies broadly to vernacular-derived building techniques. The specific artifact that the original technique used, in this case, a particular style of Tamil Nadu pot, is not what makes the technique work. What makes it work is the principle: sealed air voids, low conductivity ceramic walls, and a reduction in thermal mass. Once you understand the principle, you can find local implementations of it almost anywhere in the warm world. That is the difference between a technique and a technology. A technique requires specific inputs. A technology is a physical principle that can be expressed through locally available materials. Let's address one more practical question that comes up consistently. Can this technique be retrofitted into an existing building? The short answer is no, not in the conventional sense. You cannot embed clay pots into an existing concrete slab. The slab is already cured and solid. However, there are two retrofit applications that use the same underlying principles. The first is a clay pot overlay roof system, in which inverted pots are laid on top of an existing flat roof deck, covered with a screed layer, and finished with a reflective coating. This adds thermal mass attenuation above the existing slab, rather than within it. Performance is lower, typically 7 to 10 degrees Fahrenheit of interior temperature reduction rather than 13 to 18, but it requires no structural modification. The second retrofit approach is a suspended clay pot ceiling. A false ceiling, constructed of clay pot tiles or panels hung below an existing concrete slab at a clearance of 100 to 150 millimeters. The air gap between the ceiling and the slab acts as a thermal buffer zone, and the clay tiles add radiant surface cooling to the room below. This approach is widely used in traditional Moroccan and Tunisian interior renovation and has been adapted by contemporary architects working in North African contexts. Performance in monitored applications runs 5 to 9 degrees Fahrenheit of interior temperature reduction, which is meaningful in a climate where the difference between 92 and 83 degrees Fahrenheit is the difference between sleeping and not sleeping. Both retrofit approaches are accessible to a handy homeowner in a warm climate without a structural engineer, provided the existing roof or ceiling structure can support the added weight, typically 15 to 25 kilograms per square meter for an overlay system, or 8 to 12 kilograms per square meter for a suspended tile ceiling. Both weights are within the typical live load capacity of a residential roof or ceiling in most construction codes, and both can be combined with a reflective surface coating on the top for amplified effect. This is the entry point for existing homeowners who are not building new but want to access some fraction of the filler slab performance benefit. Let's also be clear about what clay pot cooling doesn't do, because overselling passive systems is how they get discredited. Clay pot filler slabs do not eliminate the need for ventilation. A building that uses a filler slab roof but has inadequate cross-ventilation, poorly sized openings, or a thermally heavy floor slab will not perform at the numbers we've been discussing. The filler slab addresses one pathway of heat gain, conduction through the roof, very effectively. It does not address solar heat gain through windows, internal heat gain from occupants and appliances, or heat gain through walls. In a well-designed passive building, those other pathways are handled by orientation, shading, and wall mass, and the filler slab is one element in a system, not a standalone miracle. This is worth emphasizing for anyone approaching this as a single solution fix. If your building has large, unshaded west-facing windows and poor natural ventilation, a filler slab roof will still help, but you'll still be hot. The physics of heat gain is additive. Every pathway contributes, and addressing one pathway leaves the others intact. The correct mental model is a leaky bucket. The filler slab plugs one significant hole. You still need to address the other holes. The good news is that the techniques for addressing windows, walls, and ventilation are equally low-tech and equally well documented. This channel will be covering each of them, one at a time, with the same level of detail and the same commitment to honest, quantified analysis. One dimension of this story that deserves explicit attention is the equity dimension. Clay pot filler slab construction was developed specifically for low-income housing contexts. In Oroville, in Tamil Nadu's rural housing programs, in Hassan Fathi's work in Egypt. The technique was forged in the constraint of poverty and refined in the service of communities that couldn't afford mechanical cooling. And here's the uncomfortable inversion. Those same communities are now among the best equipped in the world with a passive cooling technology that's cheap, effective, and appropriate for their climate. Meanwhile, high-income countries continue spending enormous sums on mechanical cooling systems that consume energy, emit carbon, and are increasingly unaffordable as electricity prices rise. The equity reversal is genuinely striking when you quantify it. A household in Chennai, living in a well-designed filler slab home, spends approximately $40 to $60 per year on cooling energy. A comparable household in Phoenix, Arizona, in a standard wood-frame stucco home, spends $800 to $1,400 per year on cooling energy. The Chennai household is in a hotter, more extreme climate. They simply have a better roof. This isn't an argument for sentimentality about traditional building practices. It's an argument for taking the performance numbers seriously and asking why we're not applying them where they are applicable. The barrier isn't knowledge. The knowledge has been documented, tested, and published. The barrier is inertia. The inertia problem in construction is well studied. A 2014 paper in the journal Building and Environment found that the average time between the publication of a new building performance technique in peer-reviewed literature and its meaningful adoption in mainstream building codes is 22 to 28 years. 22 to 28 years. For a technique that reduces cooling energy by 30 to 45%. The filler slab was being written about in technical literature in India by the mid-1980s. By that timeline, we should be approaching the window of adoption in international codes. And indeed, there are signs of movement. The UK's Building Research Establishment has a working group on traditional cooling techniques. The US Department of Energy's Building America program has funded passive cooling research, with explicit interest in void former slab systems. The climate trajectory makes this urgency concrete. The International Energy Agency projects that global demand for space cooling will triple by 2050, driven almost entirely by population growth and economic development in hot climate regions. Precisely the regions where clay pot filler slab construction is most applicable. If those new buildings are built with conventional concrete slabs, the additional electricity demand is enormous. The IEA estimates 4,500 terawatt-hours per year of additional cooling electricity by 2050 in a business-as-usual scenario. That's equivalent to adding 1,500 large nuclear power plants to the global grid, solely to cool buildings that could have been designed not to need it. Against that backdrop, a technique that cuts cooling energy demand by 30 to 45% at no operational cost, using locally sourced materials, and deployable in new construction, without exotic engineering, that's not a curiosity. That's infrastructure. And the decision about whether it gets adopted at scale will be made in building codes, in procurement standards, in housing finance policies, and in the training programs of construction schools. Not in research papers. The research is done. The question is whether the institutions that govern construction are capable of moving fast enough to matter. That's a political question, as much as a technical one, and it's one that communities, architects, and engineers need to be asking loudly. We'd genuinely like to know what you're dealing with. If you're living in a hot climate, if you've tried a passive cooling technique, or built with local materials, or retrofitted an existing home and seen real results, leave a comment below and tell us what you found. Not the ideal, the reality. What worked, what didn't, what surprised you. The most useful knowledge about these techniques doesn't live in published papers. It lives in the people who've actually built things and lived in them through a summer. This channel is built on that kind of knowledge, and every comment that adds a real number from a real building makes the next video more useful for everyone watching it. What began as an economic constraint, build for less, cool without machines, has turned out to be one of the most effective passive cooling technologies that engineering research has validated in the past 3 decades. The clay pot filler slab isn't the right answer for every home, every climate, or every regulatory environment. But for new construction in warm, dry climates, and especially for the hundreds of millions of homes that will be built in South Asia, North Africa, the Middle East, and Latin America in the next 20 years, it is a cheaper, cooler, and more durable choice than the concrete slab that will otherwise replace it. And that's a fact worth building on. Subscribe for more low-tech energy fixes. Next time, we're looking at a 1,000-year-old wall material that stays cool without any electricity, and the numbers are equally remarkable.